All right, looks like we're live on the air and such. New computer, under $100. Yeah, well, anyway, it's my first interaction with Windows 10.
Live on the air and such.
Oh, it's loud.
New computer.
Okay, so it's working. So I can see the chat. Everything seems to be working. Yeah, so this is all kind of amazing that, yes, in 37 minutes, it's working. Amazing. But yeah, I really don't like Windows 10 to start with, but we'll see how it goes. I was still running XP on the other computer, so I continue. I might run it on this one if I can get it to work. I might go back just so I can use my video editor and all the other crap. But I figure I might as well take advantage of this for this room and see if it works a little better. I mean, it's obviously so far seems to be working fairly well. Not too bad. So, more on the subject of light, I think. And I was watching some more of the Feynman. I've watched these lectures he's given many times, and so it's just kind of familiar. So I kind of like watching it. Just was each time you hear something a little different or a little more, and so I like that. But yeah, I guess it's just everybody else is kind of tedious. The Susskind guy is, his videos aren't much fun to watch. They really are, it's all about the math, and it's really not about anything visually conceptual, and it's all it's the abstract physics more than it is the practical physics like electricity and all that kind of stuff. So I do like other lectures just because there's more talk about mechanics, velocities and momentum and motors and all that electricity. But anyway, it doesn't really matter. I mean, yeah. So well, anyway, so it's just documentaries are almost unwatchable because they're just such piles of shit. I mean, it's just very irritating. So they only go with dinner. Is it too irritating? Well, anyway, so that's how I end up watching old Feynman ones again, just because it's easy. Because I've been there and done that. And well, anyway, so in the one he did in the 80s there at Auckland in New Zealand, lots of talk about Newton's experiments and such. And so there's one part where he mentions how Newton assumed light was a particle, or deduced, based on the fact that it creates clean shadow lines. And waves wouldn't do that. Waves would tend to bend around corners and fill gaps. And so I've always argued for this straight line force thing. So this is another one of these things where Maxwell's equations, where they drew the conclusion that light is like electricity or like magnetism, rather than the other way around, where electricity and magnetism are like light, and that they're traveling in a straight line. The straight line forces. They don't bend around corners. They don't fill gaps. And so gravity, magnetism, electricity, it's all straight line force, just like photons, like light. So instead of giving light the wave properties of these other forces traveling through mediums, which create waves when they travel through a medium, obviously, they went the wrong way and presumed light to have these wavy properties as if it was going through a medium, and it doesn't do that. It interacts with electrons, and electrons create any effect we see that we might call wave-like. Oh, it's kind of vibrating. Anyway, like it wants to collapse or something. Anyway, I don't know why it just feels more jiggly than usual. I gotta crawl under the house. It just rained, so I ain't doing it tomorrow. Anyway, I should have done it the day before, but it doesn't really matter. Different subject altogether. So Feynman's arguing in this, basically defending the particle perception. He basically says something like, well, Newton was right, but for the wrong reason, because Newton talked about the clean shadow lines as being evidence of photons being particles, not waves. And so then, but in that statement, Feynman also mentions how, well, Newton was wrong because shadow lines aren't even. There is diffraction. And so it's almost a concession that the shadow is bleeding into the non-shadow space, and the non-shadow space is bleeding into the shadow, and you have this unclean line. And that unclean line is basically the same unclean line you're maximizing the visibility of in the two-slit experiment. So it's all surfaces are creating diffraction. When light goes along the edge of a surface, it goes through a field of electrons and is diffracted. And the two-slit experiment, for example, maximizes that effect and makes it visible. But the effect still exists on a cast shadow. It's just that the effect is very small in comparison to the brightness of the light, of the contrast between the shadow and the light. As a percentage of that total light, it's too small to be noticeable, easily detected, the variation. Which is kind of a concession, in my opinion, that clearly the surface is what's causing the diffraction. It has nothing to do, in a sense, with the opening, because that just changes how far away the surfaces are, and it changes the percentage of surface to non-surface area. But that's pretty much all it's doing. It's changing how many photons will be affected, not much else. So, what do I want to make out of that? So, I mean, it's just more evidence, more reason to wonder why they just didn't draw what I think is the obvious conclusion, that photons don't do anything. Environments do things. So in this lecture, Feynman talks a great deal about the layers of glass and the Newton experiments with glass and Newton's rings, the concept, and so basically the change in the reflectivity of the glass based on its thickness. And he kept kind of weaseling out, kept trying to find excuses, not to simply state that the glass is causing the effect. The thickness of the glass. The glass is where the effect is caused. It doesn't have anything to do with photons. It has to do with structure. And you change the structure by changing the thickness. And that's not too bold a statement to make. That you have a certain number of atoms, and as you polish glass, what you're essentially doing is trying to make them all even. But maybe they can't be all even, just because electrically they're going to bond together better if they meet each other halfway, kind of thing. Like each line pushes a little closer because it isn't right next. So if I had a pen. So if I was stacking things, and things had to be a certain distance apart, you could sort of understand that if I stack them perfectly evenly, I can't fill as tight a space that if I stagger their position. So if I stagger their position, they can be closer together than if it's unstaggered. And so not a perfect drawing, but close enough. So when they're even, this space has to be larger than when they're staggered. This space can be shorter between the two. And so glass wants to have this arrangement. It wants to stagger the atoms. And so when you're attempting to polish it, what you're doing is going from a minimal amount of stagger possible to push the glass into, to the maximum amount of stagger where it, is most staggered. And that's what's changing the reflectivity of the glass, is the amount of stagger created in the arrangement of the atomic structure of the compound. And clearly that would create different surfaces that the light is going to interact with, depending on how thick, how many atoms you've knocked off, in a sense. Something like that. So where do I want to go with that? Yeah, so it's something like that. It just becomes a cyclical thing. Each time you take a row of atoms off, you go through the cycle again, and then the next row of atoms, and cycle again, and the next row of atoms, and cycle again. So with every row of atoms, you just recycle through the same uneven imperfection in the surface. And that creates the phenomenon where you go from a 16% reflective index to a 0% reflective index. Although I think the 0 is pretty hard to actually achieve in practical reality. Anyway, might be unrelated. So, what did I want to? So it's just another reason to, recognize, that there's mechanical explanations for these phenomenon, that they turned into mystical functions of the universe, as if it was a real probability, and it has nothing. There's no such thing as a real probability. There's only inevitability, and probability is just a lack of understanding of the circumstance. And the circumstance is that if you could have a photon hit exactly the same spot each time, it will do exactly the same thing each time. And so the probability would be 100% reflective if you could actually hit the same exact spot on the surface of the glass. That one spot would be 100% reflective. And the spot right next to it might be 100%, 0% reflective and 100% transmittive. Something like that. So what else do I want to say about that? Just compiling all these different elements, into a coherent description. The other part I was thinking about is, again, this energy conservation and the whole idea of what happens when a photon goes into an electron. That it gives the electron directionality. It gives it acceleration. Let's put it that way. It accelerates the electron in the direction the photon was going. And through that process, it is releasing polarization. It collected photons of a certain polarization. Those photons will have to have the same polarization as the electron, so they're being converted, and that conversion leads to the expelling of the other polarization through the tangential dimensions, when you're getting rid of the stuff. It's like the electrons have to stay, they have a size requirement. So if they gain something which gives them velocity, it means they have to give away extra. They have to give away the same amount of energy. That's not the right way to say it. They have to give away. The polarization is really all they're getting rid of. So it's always going back to this polarization argument. So when the electron is accelerated, that's when it produces the magnetic or electric phenomenon, the fields perpendicular to its velocity. And that perpendicular release isn't really a release, it's just a conversion of polarization. So while the electron is moving, I think it's only while it's accelerating. While it has velocity, it's not going to produce the effect. It has to be acceleration. So it has to be while it's gaining photons that it will release the polarization of those photons, as those photons will now gain the polarization of the electron, and it will release that eccentric polarization. Then the off polarization is released through the tangential dimensions. See again, it's not released, it's converting what comes through, what goes through it perpendicularly gets converted. So yeah, I have to say that more clearly. I mean, I could try drawing a picture of it. But it is always perpendicular, and it's not a gain or production of energy, it's only a conversion of the existing force into a polarized force. So it's just converting the gravity that's mixed polarization to a force that's of one polarization. Let's see, so how does it accomplish that exactly? That's the mechanism issue that I have to come up with. But I think it can be seen as like the spokes of a wheel. So the electron has a rotation, and when something goes through it sideways, it will hit one of those spokes and shoot out something that's in a spoke position. So it's that polarization. But where does it get it from? How does it maintain its... It has to keep filtering. So, I mean, it's changing the polarization, which means it has to be, if it's letting everything go in one polarization out of its perpendicular dimensions, it means the polarization that wasn't that polarization has to still be in the electron somehow. So that's the part I got to explain. I have to think about that one. It's probably because they fill the range of polarizations, but I don't know if I want to get into that. So yeah, so I'll write that down. That I still have to work on the accelerating electron, which is an electron absorbing photons. Okay, which means it absorbed their momentum in a direction. Because it's going to, if it releases them, then it'll stop that acceleration. That's how the acceleration, it gains the acceleration, which is converted into a velocity. And so the velocity is given, so the acceleration is maintained as a velocity, an increase in velocity. So that's what acceleration does, an increase in velocity. And then it releases, when it releases the photon, say like in the example of glass, where the photon goes through the glass, transmits its energy through the electrons, then the electron emits the photon at the other end. It gives back the velocity. And so that's the equal but opposite reaction. Okay. Now the question is, during the acceleration process, the electron converts gravity going through its perpendicular dimensions. It changes the polarization to, whatever pole of the magnet it would happen to be, or whatever plus or minus charge. Okay. So I still have to come up with the only way a photon could be absorbed is it has to be coming in the same direction as the current. The frisbees have to be the same. I mean, if we think of an electron as a galaxy, it has a plane to it, a flatness, and the photon has to be coming in at the same vector. Yeah. So I'm just trying to think of whether it has to be, the photons would all have the same, the tons of the photon would all have the same polarization, but I wonder whether the polarization has to be the same as the electron, because I'm still trying to figure out the mechanism of the conversion, and whether the conversion is an exchange of polarization or an actual conversion where the universe is actually creating an imbalance in polarization. Let's say the universe started off with just as many things polarized in this direction. Sorry, I'm forgetting that using this camera. Just as many things in this direction as this direction as this direction. So if you thought of it, the universe starting off with an equal amount of all of those, you can either argue that they're exchanging them. That is, whether if something admits one going this way, then it had to absorb one going this way, or whatever the opposite would be. Or whether you can change polarization from, say, this to this without any losslessly, without any consumption of energy. So that would be the question, is whether polarization is something to be created without having to expend any energy, just through the normal interaction, and it just consequentially produces polarization. So it might be that polarization doesn't require any energy. It doesn't require any energy to convert a photon from this to this. And that sort of would makes sense, because there's no obvious heating or energy consumption. Nothing's destroyed when photons go through a polarizing filter beyond the amount of photons that are destroyed by the filter. The bars itself are wiping out some of the photons, but there's no energy used to convert the stuff that is almost the right polarization. Is all converted to the one polarization, so that doesn't take any energy. So it's like if I'm throwing frisbees at the jail bars, and I'm throwing the frisbees at kind of not perfectly straight angles, they squeeze through the bars if they're close. If they're this, they're going to get blocked. But if they're this, they'll squeeze them straight. So the bars will actually bend all the frisbees into one perpendicular polarization. All right, so that makes sense. So it doesn't, so during acceleration, something happens to the electron that allows it to convert the mixed polarization of the gravity. So the gravity is coming in at all kinds of different polarizations, and it converts that mixed polarization, all of them, to one polarization. I see, not all of them. It could just be the ones that are close. So it takes, say, 25% of the gravity and makes it one strict polarization. So it acts as a polarizing filter when accelerating. So that's a good way to say it. So an electron accelerating becomes a polarizing filter for any ton traveling through either of the perpendicular dimensions. And the faster the acceleration, the faster the electron is being accelerated, you could almost argue that the capacity to do that polarization becomes less and less. I'm just trying to think of because the amount of elements in that dimension are becoming less and less. I mean, as you accelerate an electron, you start to lose your dimensionality. So you go from I think I kind of like this metaphor of the tank tread. And that if I made the tank tread very tall, then it would move kind of slowly. But if I make the tread very long, then it'll move very fast for the same, you can't say the same amount of rotation, because it would still be, it still would add up to this. See, I have to think about that. I mean, I have to see, this is where you have to visualize things, and it gets kind of complicated. I mean, the surface area is still the same surface area, no matter what shape the circle has. So, in a sense, that's not a very good metaphor. Yeah, so I have to come up with a better metaphor for the fact that the wheel is getting flatter as the wheel accelerates. Yeah. It's losing its up and down, and it's left and right when it's going forward. So forward is this way. It loses this and this. Obviously, when you're going the speed of light, all the bits are doing this. None of them are doing this, or this, or this, or this. Obviously. So I still have to think on that one. All right, so the question will be, you see, there's no effect. If I put electricity through a wire and then I take a magnet and try to induce electricity, I can induce a current added to the current that exists, but I don't think I'll do much to stop the current that exists. I won't affect electrons already accelerating. But I guess it would depend on the strength of that magnet. I have to think on that one. It seems like there's a real, there's some reason, I have to think about it, but where the force of magnetism, or an EMF field, can't affect a electron with velocity. I'm just thinking of the example, like I could take a magnet and I could put it next to an electronic device and I won't screw up the device, it'll still work. So I won't be pushing the voltage out of the wires that the voltage is traveling through. Where if I take a wire with no moving charges in it, it will induce the movement of the electrons. It will accelerate them to essentially evacuate the wire. Yeah. So I have to figure out why that is. So yeah, that's a question mark. Why are accelerating, let's see, why are moving, not accelerating, moving electrons. See, it's really a question of whether the electrons are moving or whether the force is moving between the electrons. Like they're just passing on the photons of the electricity. Why are the moving electrons not affected by EMF? Something like that. All right, it's like charges repel, then why do photons stick together? Protons. Well, you say protons stick together, and they don't. They also don't like each other. So that doesn't make sense. I mean, I think that's what the neutrons are for, is to create a mechanism to hold the protons together, you know, to hold them in the same arena. So, I mean, I'm just saying that's probably their function. In most cases, right, you can't live without the neutron. The only place you can live without it is like hydrogen or something, right? I mean, you can have a hydrogen atom without a neutron in it, right? I think. But I mean, bigger atoms, you have to have neutrons. So the neutron's probably playing a role in, it's not as neutral as it sounds, I guess what I would argue. The neutron isn't really neutral. It's, let's see, what's the right way? Well, maybe neutral would be the right word. It's halfway in between an electron and a proton, right? So it still has a charge differential with the electron and has a charge differential with the proton. So it is a attractive element to protons, but it's only half attractive, and it's a half attractive to electrons. So being a neutral doesn't mean you don't have charge relevance. It just means that you're not a full opposite charge. Yeah, so that's probably a good way to say it. So there's a half charge attraction between neutrons and protons, and between neutrons and electrons. There's a half charge attraction. Yeah. Yeah, I'm just trying to think it through. Yes, it's the only one that's the same charge as the repulsion. So there has to be attraction when they're not the same. And the neutron is not the same as the electron in charge, and it's not the same as the proton, so there has to be attraction. That's an easy deduction, yeah. Well, I mean, isolate is a tricky word. I mean, obviously they can control the emission of a neutron. I mean, that's what an atomic bomb is doing, basically. It's causing a neutron chain reaction. So that's what causes a nuclear explosion, is you're sending a neutron into the nucleus of an atom, and the neutron is basically causing the atom to break down and release 3 more neutrons. So, you know, with uranium atoms, I think it's 3. So for each time a neutron goes into the uranium atom, it releases 3 neutrons. So you can see how that would add up to disaster pretty quickly if each one of those 3 then will create 9. And then those 9 will create to 28 or whatever. So, I mean, it just keeps multiplying and causes the chain reaction of breaking down all the atoms because you keep creating more neutrons, loose neutrons. Well, I'm just saying that we know what a repulsion is, right? If we say repulsion, so the question is, how could it attract both? If we know having the same charge is repulsion, and I'm just saying, if you have an uneven charge, that would automatically indicate a kind of attraction or less repulsion. I mean, I see what you could argue that if you have a half of an electron, there would still be a negative charge, and negative plus negative would be repulsive. So that breaks down a little bit, but it all depends on whether you think there is a real distinction between positive and negative, where one is zero. So I guess what I'm arguing is one is a zero state and the other is a higher state, some plus number. So the plus is sort of theoretically infinite. If you could create a good enough insulator, you could create a huge giant voltage potential. So the voltage potential, the charge in absolute sense, could be anything. And so if you think of the electron as being the zero and the proton being 10,000 positive, you clearly could have something that's 500 positive that would still be attractive to the electron, but it would be unattractive to the proton because it's still negative compared to its positive, and it's still positive compared to the other things negative. Yeah. So I think it is linear. So I don't think that you could have a half an electron. If there was such a thing as a half electron, it really wouldn't be qualified as saying, you couldn't say it has a negative charge. It only has a negative charge relative to the proton, but relative to the electron, it has a positive charge. You get it? So it really is strict. So it's only same charges that are repulsive, and anything that's not same will be attractive. I'll have to think on that. I'll write that one down. Same CH charges are repulsive. Anything unsame would have to be attractive. Because the potential is lower. It automatically has to be attractive to a charge because it's a lower potential. But it's still higher than the proton. See, that's where I'm, okay. So if I'm half of a proton's positive charge, then I'm still attractive to, obviously I'd be attracted to the electron, because the proton's already attracted to it. So that works out okay. And if I'm only half as positive as a proton, it'll perceive me, right, as a negative, I think. Yeah, so it's just this linear argument. If I'm, whatever that is, try office. No, I'm not going to do that. That's something annoying Windows 10 does. So anyway, you were lagging. Great. I was probably lagging because it was trying to sell me a product. It's just it's just so stupid. I mean, like I said, I really can't complain though. This is really quite a nice computer for under $100. Anyway, can you repeat your idea on the neutron and how it can attract both? No, I'm not going to do that. Because I'm not sure of it. I guess all I'm saying is if the nature of attraction is a difference in charge, if something's less positive than you, it'll look negative. If something's more negative than you, it'll look positive. Something like that. Oh, you were lagging. Oh, okay. That makes more sense. Are all protons equal then? There seems to be a tendency here, but by equal, you could argue that galaxies have a certain range of size in space. That they've found a couple of these mega giant ones, but they're still not like 10 million times bigger than the other ones. They're like 10,000 times bigger or something, or 1,000 times bigger. I don't know what the exact number is. So you could say that there's a range, because we really can't measure that accurately enough. But it does seem like photons are photons are photons are photons, right? It's all the same ton. It's, and it's just the same thing. And so, it seems like electrons have this same kind of mechanism where they can't gain. Let me see. See, I'm trying to think. I think they really do. They can't gain mass. So I think they really are rigid. And so I think when they do get accelerated, they have to release mass in the tangential dimension. And then when they release a photon in the forward direction, they have to absorb mass in the tangential direction. So the deceleration causes a reverse in the polarity of the field created around them. So yeah, I think that has to be. I think that is probably a rule. So I think generally speaking, I would argue that all these things are made out of these tons. So the electron would be a hurricane, and then a proton would be an even bigger hurricane, but spinning the opposite direction. Something like that. And the spin that's creating polarity, or you could even argue it's the angle they're spinning at. The proton is, spinning this way. The electron is spinning this way. And somehow the electrons spin around the proton. There's some kind of configuration, some geometry that holds them together. Because of the fields created around them and what they're expelling. And again, they do this expelling out of the tangential dimensions. So whatever way they're moving, it's the perpendicular dimensions where they're releasing any force that is going to hold them together. And the force, again, is made out of these little tons, the gravitons that are really just a form of photon that doesn't have a frequency. And therefore it can't get absorbed by an electron. It can only pass through an electron. Okay. Yeah, so I still have to figure that out, whether there's a real, the idea of the polarity being reversed when the electron is accelerated because a photon came in moving this way. It gave up ton this way out of its perpendicular dimensions. So it can do this forward thing. And then if it releases a photon in the forward direction, that will stop its acceleration, its velocity, and it will force it to absorb tons in one of the perpendicular dimensions, creating the shadow effect, which is attraction. So when they decelerate, they create attraction. When they accelerate, they create repulsion. So the force is going out when they're accelerating. When they're decelerating, the force is going in. So it's the positive, it's like regular gravity when they're decelerating, in the sense that it's the shadow idea. The gravitons don't get through. They're blocked. They're absorbed. And the extra ones are admitted when it is accelerated. Okay, so that might be the way to do it. So acceleration causes out. Causes out, and then deceleration, that is admitting a photon in the forward direction, causes it to absorb to. So that is in, or absorption of perpendicular. Yeah, so anyway, that's really is, these are really important technical aspects that I really have to start getting right. If I'm going to, I mean, I just have to do the more worky part of making sure I'm saying it the right way. I think the school of fish analogy does enough to give the idea of it, where you can kind of understand if there's 1,000 fish, and there always has to be 1,000 fish, and I put 2 fish in going one way, that I have to take 2 fish out going some other way. And the school will slowly move in the direction that I put the 2 fish in, theoretically. Yeah, well, 400,000 doesn't sound like all that many years, right? I don't think that it happened that way. I mean, I don't think the Big Bang was photons, because I don't see how they could possibly condensate. I mean, if you think about an idea of a plasma exploding, or just photons with individual vectors, as they get further and further away from the ground zero, the bang, there's less and less chance they'll intersect with each other, because the distance between them is increasing, not decreasing. So it's pretty hard to understand how the Big Bang actually works, if, in my opinion, unless you put a shell around it. So I think the Big Bang already had to have some kind of something to create the pressure. It's like a pipe bomb. There's no pipe bomb unless you have the pipe. Without the pipe, there's no bomb. Yeah, pretty much. So I'm not too sure about the Big Bang. I'm certainly not convinced that these super dense objects that we see, 15 billion light years away, could have gotten where they are, so to speak, in the condition they're in the day after the Big Bang or something. And it took 15 billion years just for them to get where they are, probably. So any estimate how old the universe has to include how long it took the stuff to get to those positions or to get to those sizes. And it sort of doesn't make sense intuitively to argue that these supermassive objects that we see very, very far away, they're supposed to be very, very old. Well, they have to be, or could possibly have been formed in an early stage of a Big Bang. They're late stage objects, not early stage objects, if you think about it. I mean, early stage would be blobs of gas that galaxies are forming out of. But that stuff's not 15 billion light years away. I mean, it doesn't need to be. It's much closer. So that's a function that's happening all the time. So, yeah, I'm uncommitted to an opinion on whether you need to have a Big Bang at all. I think they're miscalculating redshift, and I think that's causing a lot of problems. Because I think they're assuming they understand redshift when they don't. So they're doubling the speed of stuff in the universe, which I think is breaking a lot of their math, because that's why it doesn't work, is because, they have over perceived the actual speed of things. So I think redshift can be created two different ways. I mean, I think it is a function of time dilation. When the metabolism of the thing producing light is slowed down, it's also going to slow down the frequency of the light it's producing. So just as you're getting cryogenically frozen, you start talking slower. Well, you would start producing photons slower too, causing the redshift. So something going sideways to you could appear redshifted, like it was going away from you, when in reality it's just that it's moving fast sideways, and it will cause redshift also. Once it's a sufficient enough speed to cause some time dilation. Yeah. So, yeah. Sorry, I am getting tired. Yeah. Too early to quit though. So maybe I get a second wind. Or something like that. Yeah, this new computer is dead quiet. You don't even hear it. But yeah, I wish this. I wish they get. Maybe somewhere on Windows 10 they give you some kind of option to view things the old way. I'm just looking for things like, system, something where I can't even find where I can find out what this computer is. Where do I find what the computer is? I mean, they don't have like a device manager thing here or something. It's like, just not as obvious. System. Well, there we go. Let's see what that says. Change the size, text, apps, and other items. I don't want to do that. Customize your display. I don't want to do that right now either. Default about. Let's go to about. Yeah. There we go. Yeah, so it's a Pentium J2900. I wonder what that is. Never heard of the J thing. It's supposed to be a quad core. Does it say that somewhere? No. It should though, right? How do I see it? Well, I guess maybe I can. Well, I'll look at this stuff later. What am I doing this now for? Let's see, related items. There's device manager, but I won't bother there right now. Yeah, I wish they had more on the CPU. Well, it must. System info. There's some more system info. It just doesn't say anything. Advanced system settings. Oh, no, I don't want that. Oops, my mouse has failed to move properly. There it goes. It's got all these extra buttons on the mouse. I don't know what these do. Yeah, what do these extra buttons do? Yeah, I mean, not doing anything. Yeah, I have to figure that out. Anyway, I'll leave you alone. Device manager. Well, I guess I should look in the device manager. I'll be able to see what the CPU is. Theoretically. Let's see. Imaging, mice, monitor, processors. There we go. Ah, yeah, there's 4 of them. Okay. Excellent. All right, so enough playing around. Here, all this crap. Where was your load crap? You're stuck with it. Win plus E to get to your files. Win plus E. I don't know what that means. Oh, the Windows key. Okay. I've never even touched a Windows key in my life. It's just kind of funny. But yeah, okay, I'll try that. Yeah, I just like I really like the old, 3.1 Windows, whatever. I mean, the old style. It's just, I like to be able to see my files. I like to see the whole name of the file. I like to see the dot file name. I mean, it's just, I hate the way they make everything, whatever it is, imbecile. Like, I don't, I don't like the glossy lack of detail. But anyway, it's just me. This mouse doesn't like you using a piece of paper that moves. It's kind of funny. Some mice want the paper, some like the surface better. Yeah, it doesn't really work at all on this desktop. It really does need a piece of paper or something. A fake pad of some kind. Yeah, it's a little sloppy. What's this little button up here do? I might change the DPI. There's a button on top. Anybody know what that does? Yeah. Can't make it do anything. So, well, anyway, so I got 3 extra buttons to figure out what the hell they do. Probably turned off the volume or something. I probably already did something stupid, so I shouldn't mess around. All right, so let's see. Do I have more strength to say more about? Well, it's all straight line force, and so the real thing isn't understanding photons. The thing is understanding that all force is like light, except it's invisible. So if you could make all the forces visible, well, it's even like light, though. That wouldn't help you too much, right? Because the only way you see light is when the light goes in a wrong direction. So you only see a laser beam because some of the light hits dust and then reflects to your eyes. So it never got to the destination. So you're not seeing the light going somewhere. You're just seeing a piece of the light getting consumed by your eyeball. So in that sense, you're not seeing the force. You're interacting with the force and such. Yeah, I don't know. Maybe they're game things. I didn't think of that. Yeah, maybe they're extra buttons for jumping and things. Yeah, I don't know. I mean, it's not that kind. It's got this stupid arrow. What I mean, all the stupid thumb hole on the side, and so it's got 2 buttons over here, and then it's got some little dopey button here on the top. I don't know what that one's doing. I mean, sometimes those are DPI buttons. You can change the DPI, but I don't. Nothing flashed on the screen. So maybe maybe I got to find the Dell software, and load it. Duh. It doesn't say Dell on the mouse. Search. So It looks like a Dell thing though. You know, it matches the keyboard, and that says Dell on it. So it must be Dell authorized. Well, it's conductors. Conductivity is conductivity, right? So when you touch the fence, the salt in your skin goes into the water on the fence, and it creates a better conductor. So you get more of the electricity because the salt spreads into the water and makes it more conductive. So the better the conductor, the more electricity, you know, that kind of thing. And such. And so forth and whatnot. So, what is this? I'm Cortana. Ask me anything. What's a Cortana? Microsoft is really queer. Why would what do you mean ask you anything? How can I, you know, trip Bill Gates and make him fall down and hurt it himself? I mean, what was ask me anything? I mean, just what is that? Ask me anything. Yeah. Yeah. So, gee, it's not so hot in here. It's really quite cool now. I'm still kind of hot. I hope I do my temperature thing. Make sure I don't have a fever. Anyway, I'm getting tired. Just saying. So I'll probably bail pretty soon. Somebody shows up in the talking mood and such. Yeah, well, I figure it does searches, but I just find it kind of obnoxious that it takes up so much space. You know, it's just kind of like rude. Like, why would I want that thing sitting down there? That's okay. I mean, it's just kind of funny too, because you know, Windows 10 startup, you know, they ask you, you know, they like talking to you, like they write stuff on the screen, hi, you know, blah blah blah, little conversation kind of stuff. You have to fill out a couple of yes or no questions, and you know, become a friend of Bill Gates or whatever, and Facebook him and stuff. But whatever. But the funny thing is it does that before it does your hardware profile. So, you know, my mouse didn't work. It's like they didn't really make it keyboard friendly. You had to keep using the tab button to get to the, you know, it really was kind of stupid. Like they should know whether I have a mouse that works, you know, but it's not plugged in. It's a, you know, whatever that is, a Bluetooth thingy or whatever. Just seems kind of stupid that they have a form that's really kind of, I mean, the next button is all the way over there. You really can't get to it with your keyboard. But anyway, you know, I'm not here to talk about Windows 10. I only have limited experience with it anyway, so I can't really judge. And like I said, I might not even have, you know, it might be very limited because if I can get my XP hard drive to run and get the drivers to work, I'll probably just do that. Although it would be interesting just to see what a 64-bit OS does in terms of, I'll have to see. I'll have to see how many browser windows I can open and how fast they'll jump around and all that shit. I mean, I wish I had video editing software I could load on both computers and just do a real test, but I don't. So I won't. So I don't know what that means. The search engine is like a personal computer, Google. Not a proper sentence. So anyway, yeah, so kind of a whatever. Yeah, I just had this stuff on my mind, so it was worth talking about because I really do see where I just have to do more about this difference between an accelerating electron and one that already has velocity and field implications. Because you really only have the EMF if you change the polarity of the electricity. So once the electrons are moving, they're not creating any field. So they have to keep accelerating. And so you can keep accelerating constantly if you keep changing direction. Because then you're accelerating, decelerating, accelerating, decelerating. Because decelerating is the same as accelerating. So you're in a constant state of acceleration if the polarity of the electricity is alternating. Where if it's DC, you're not in a perpetual state of acceleration. You're in a perpetual velocity, and so you're not creating any EMF. Yeah, so that's a good way to understand it. Okay. So I just have to build on that. So, yeah, I mean, doing these rooms is really helpful because I just go through my own thought processes, and so I think I can make better arguments in the future by going through this laborious process of thinking these stuff through in some sort of where you actually have to say it way. Because sometimes when you're just thinking it, you're not thinking it through. When you actually hear yourself say it, you say, wait a minute, that doesn't quite make sense, because you actually hear it. Yeah, sometimes you need to hear it to know how stupid it is. Yeah, something like that. Yeah. Yeah, I got some new nicotine juice today, and I got some menthol crystals. So they're kind of nice. So I usually don't use flavored vapory stuff, but yeah, the menthol's not bad. But I will probably use it to excess. Yeah, I'm thinking, yeah, I gotta put a couple more crystals in there. Yeah, a little bit stronger would be good. Yeah, I'll end up making it too much. But I like it that way, sort of. So that's not necessarily a bad thing. All right, let's see if I have any other news. Yeah, all my websites should blow up any time now. This GoDaddy will cease to. Well, my old account will be destroyed, and I'll have my new one, and then I'll have to switch everything over. So, but I just figure I'll take it one site at a time and try to rebuild them in a new and better, new and improved way. something like that. And anything else? There we go. I think it's like, oh, okay, that's the iPhone thing. Yeah. Yeah, so I guess Microsoft is still copying Apple or something. Yeah, well, I don't know about this expansion thing. Like I said, that's part of their miscalculation regarding redshift. If they've overestimated redshift, then obviously their understanding of this separation would be exaggerated, and so things aren't moving apart. Frankly, I don't think the expanding universe makes any sense, really, right? Because the universe inside of atoms is the same universe that separates the Earth and the Moon. And if you start thinking about everything moving apart, especially in the atoms, you could see that that's not going to work, because this is all based on fields, and the fields would all break down. So it sounds kind of not right, because if space is expanding, then, like I said, Pluto is going to fly away. Things will lose their connection to the other things. So I don't think that's right. I mean, it would only make sense if you thought the Big Bang was a really slow explosion. Really slow. Then it's sort of, you could make sense out of that. Because as it gets further apart, it starts separating. But I mean, it still doesn't make any sense. Unless there was a really slow explosion of very big things, like the moon blowing up into 5 pieces, and 5 pieces break up a little bit, and then those pieces break, so it starts breaking up as it goes further out, rather than starting off as very small things. So it's almost like you have to think of the Big Bang as being big giant chunks accelerated, and then the chunks fall apart through the acceleration, and something like that. So I don't think it works. Yeah, I don't think I'm just saying, I just don't think that works mechanically. I don't think the universe could be 15 billion years old if it was still expanding at anything near the rate they claim. There's just so many elements to it that are very complicated. There's all these big things moving very fast. It's very hard for a big thing to acquire velocity in one direction, right? So to move a big thing in one direction to get it to a high velocity means it has to either collect a bunch of stuff that's already moving that way, or it has to be hit by a lot of stuff going that way and not going the opposite way or some other way. And so velocity is a hard thing to acquire in a neutral universe, because it would require quite a bit of force to have velocity. And so you can see that big chunks of like a supernova exploding, you can understand how a big chunk could have a pretty good velocity. But we're talking about things bigger than suns having very high velocities. And I would argue, where did that energy come from? I mean, how did it collect all of that force in one direction? Because it had to collect it, had to acquire it somewhere. It didn't just happen to have a velocity. It had to collect the velocity. So that's another piece of physics they got to fix. Is that just don't make sense. Big things don't move fast. Little things move fast. I mean, clearly we're moving much faster than the sun, and the moon is moving much faster than we are. I mean, everything, as you get smaller, the stuff goes faster because of the, we're moving as fast as the sun plus the orbit of the Earth. The moon is moving as fast as the sun plus the orbit of the Earth plus its very slow orbit. So anyway, I probably should have done 2 of these in a row. So I am tired. Yeah, I didn't sleep very much last night. And so, yeah, it's kind of silly. In a way, kind of. Make it a little bit. All right, so sorry, not a great deal of physics in the last half hour, but, it happens. I gotta figure out what these extra buttons do. All kinds of missions I can go on now. But yeah, I'll be curious if I can run my XP on this computer. But I really should see what it does first. I have to find some way to test its speed and such. Yeah. So anyway, oh, there we go. How come roller coasters make you feel sick, but moving at 2 million miles around the sun doesn't? At 2 million miles. 2 million miles, what, an hour? I don't think we're going that fast. Yeah, well, that's just the issue of, because of the roller coaster, we're in very strong gravity on the surface of the Earth. And there's the force you would feel from the velocity of the Earth doesn't have anything to do with that gravity. So it's only the gravity that makes the difference, right? So without the gravity, you would be in a constantly weightless state. So no matter what your velocity, you wouldn't notice it. But I mean, materially, you would notice it because your material form would start to degrade as you go faster and faster. All the atoms become misshapen, they stretch out, and you would die. So you would definitely feel sick first. If I moved you very fast, 100,000 miles a second, yeah, you're not going to be in very good condition. But the very relatively low speeds we're moving at by comparison, I mean, if you collected all our rotational speeds, it probably still only adds up to like whatever 100,000 miles an hour, compared to 3 million, that light's moving a second, meters. So it's just, but yeah, it's just a gravity thing. See, we're in as far out as the Earth is, the gravity effect from the sun is incredibly weak, and we just don't realize that the surface gravity here on Earth is 10 meters per second per second. of gravity from the sun at this location is 0.003 meters per second or something like that. It's incredibly small amount of gravity that we're actually feeling from the sun. So obviously when we're moving through that gravity, it's such a weak gravity that we can't detect the change. The interval of change in speed. I don't know exactly what that means, but change is acceleration or deceleration. Acceleration forward or backward. Get a good hit off of this thing for some reason. Yeah. Battery's weak or something. Huh. Anyway, not your problem. No, it's not really the change in speed. It's the change in your orientation to gravity. As the roller coaster changes its position, the gravity of pushing on you is pushing on you in different positions. And clearly, if you go upside down or something, the gravity is exactly the opposite. So, yeah, that's what's making you feel sick, is that your internal organs are moving in different directions and they don't like it. Yeah, I picture your atoms splitting light, spitting, to accelerate you in other direction. Yeah. Well, what I'm saying is you have to sort of think of the thing has to roll, and for it to roll in a direction, there has to be an imbalance. So it has to stick to the surface. So if you thought of a perfect circle, you could almost say that there's only one spot hitting the road, right? If I make a perfectly flat road in a perfectly round circle, I only have one millionth of that circle that actually is hitting the road. So there's very little friction, so to speak. And as I flatten the circle, there's more and more friction. So you can get the idea that the spin would cause it to roll, kind of an idea. I mean, I'm not saying there's an ether or a road. I'm just saying the idea is that more stuff is going in the direction of your velocity, and you're constantly reshaping your eccentric orbit in a new position. So even though you're still traveling in a circle, you're traveling in a circle that keeps going forward. So the real shape of the circle is deformed lengthwise. So it looks like a circle from your perspective. But if you saw it over time, you would see that technically it's misshapen because they're all ellipses now. And so your ellipse gets wider and wider and wider the faster you go. You're basically just losing those perpendicular dimensions. And like I say, if you get up to the speed of light, you've lost all your perpendicular dimensions, and now you only have mass in one direction, forward. Let's see, different directions relative to just standing still. Well, it's always just relative to some other position, but I'm just saying it doesn't matter whether you call it standing still. I'm just saying your velocity is absolute. It's a real thing. You have an absolute velocity towards, relative to a dead piece of space. So yes, relative to something else standing still, you have an absolute velocity that has an absolute vector. And it just keeps getting bent because of the gravitational fields you're in. each field is bending you in some direction. Different direction relative to current directions. Yeah, well, technically, there's no you, right? You're just a pattern. And all the stuff is moving, and you're just the color of the stuff moving or something. You're a pattern. You're not really stuff. So you've been filtered out of. So it's like if I said this the other night, but I mean, you could take the pixels on a screen, and I'm just saying if you randomized all the colors, and then you could make it appear like the pixels are moving across the screen, when in reality all you're moving is the color. So as my hand moves across the screen, the pixels that are on my hand over here don't actually move over here, just the color moves. And that's kind of how we're behaving. We're not really matter moving, we're just polarization moving. So the current direction is based on the Earth's movement. Well, I'm just saying it's one level compounded on the Earth's movement. So it's everything the Earth is doing plus what you're doing. So it's always the plus thing. We're stuck on the Earth. We obviously have every bit of velocity the Earth has. We have exactly that same velocity. Plus, if I run that way, I have more, I have some little extra. I'm going a little faster than the Earth then. If the Earth is moving left at 100 miles per hour, then I move right at 1 mile across its surface, my brain will get jostled. Well, I mean, that gets a little complicated when you start talking about the rotation or the spin of the Earth and counterbalancing the spin, because you're only counterbalancing, like obviously half the Earth in a spin situation, half the Earth is moving one way and half the Earth is moving the other way. So they're undoing each other. One's going forward, one's going back. So when a sphere spins, one side of it's going forward, one side of it's going backward. So it's conservation. So it's not really moving, technically. Let's see, the roller coaster is slow, but again, this doesn't matter. The gravitational g-forces aren't slow. So I'm just saying it's how many times you're going against gravity, like you're accelerating against the gravity, and then accelerating with the gravity. You end up doubling the effective force, right? So it's you're just never balanced to the gravity, and that's what's making you sick, is that you're constantly not at balance with the gravity. So it's moving your junk because you're constantly accelerating and decelerating inconsistent with the 10 meters per second that gravity wants to move you in one direction, and you keep going kinds of directions. Yeah, well, it's not necessarily temporary, because acceleration leads to a velocity, and the only way you get rid of the velocity is to have a counter acceleration. So not necessarily temporary. Why would it have so much effect? Let's see, but it's so slow. Why would it have so much effect? Well, I guess the gravity thing. Your system is habitized to a standard gravity, and you're obviously changing your orientation to that standard by being on a roller coaster, and your system doesn't really know what to do about that. Yeah, well, to have any real substantive change, you have to go very, very, very fast to start really deforming atoms. You're talking about incredible speeds, speeds we'll never even come close to even imagining. I mean, the fastest thing we can make goes, what, 50,000 miles an hour? Not very fast. I mean, compared to 386,000 miles a second, uh, you know, 50,000 miles an hour is pretty fucking slow. Anyway, Oakley doke. Really am tired, so I will be back. Who knows when? Somewhere in the next day or two, and try again. And continue to try again, and again, and again, and again. So anyway, I am looking for debunkers to give me real arguments about why it's not possible for what I have theorized to be the correct explanation of our reality. So, and I broke the mouse. Cool. Yeah, otherwise, hello, mouse, come on. What are you doing? Not moving properly. Maybe it's one of these buttons I shouldn't have pressed. It really is broken. Let me try turning it on and off. Maybe the battery's getting low or something. There's a free battery. All right. I don't know. Anyway, I think I'm back. I don't know if I was always here or not, but anyway, something went wrong. So I think the battery on my mouse is weak or something. I don't know. It keeps fucking up. So a Windows 10 feature. And I don't know if I don't have any batteries like handy here. They're all dead. Yeah, let me try this one. Let's see if this is the problem. I think it's the problem. Oh, come on. Second thing open there. Only thing wrong with this very nice computer is that they give me a shitty battery, maybe. No, that battery is not any better, apparently. Yeah, this is going blinky, blink, blink. Blinking at a very high rate. We got a battery in backwards. No, I got a battery in right. Oh. Yeah. Gotta quit leaving batteries in the recharger when it shuts off because then it just kills the batteries. Okay, that looks a little better. All right, so anyway, yes, so we've done our job, I think. So I'll end this now and say thank you very much and so forth. And I can't see the chat, so I don't know if anyone's chatting. I wonder if this chat inside the room is still empty. Yeah, I don't know what that's for. But no one seems to be able to access that, so useless. Anyway, till next time and such.